Okay, let's start. Do you remind me when should I announce the midterm? What's the date I should announce the midterm? 27. So what's the date today?
23rd.
Oh, that means I only have 4 days to prepare. I have not done it yet. Okay, so midterm. So many people come to ask me what's the form of the midterm. I have no idea yet. I have not prepared the midterm yet. But it's mainly about the calculations, some numerical calculations, some derive some expressions. Yeah, probably that's much. So the probably 1 or 2 discussion, but not too much. Okay? The reason is it's easier for me. When your discussion, I need to go through your word. Okay? Some of you guys have really nice handwriting. Somebody knows. Okay? So I have no idea what's going on there. And some vocabulary I have no idea. I need to go to the dictionary to see what's going on there. Forget about that. I try to dump the image to the ChatGPT, but ChatGPT cannot recognize the handwriting either. So I think it's probably better for us to just do the calculation, so I can see the number. Okay? But I can easily know that from the whole first homework. I have not graded the second homework yet. I have not just got no chance, no time to do that yet. From the whole first homework, I know that somebody uses ChatGPT or Gemini to do the job. Because the reason is, your question is so perfect, too real, too good to be true. Okay, let me give you an example. Okay, so if you do this one, you know that I'm talking about you. But I did not remove any credit, but I don't want to see this in midterm. For example, I asked you to calculate the gamma. You know that the CP divided by CV or whatever. For the adiabatic process, okay, the PV gamma equals constant, right? And then something, remember last time? And the gamma for the ideal gas is how much? It's 5 divided by 3, right? And I already told that it's for the ideal gas. And you can see the homework, okay. If that is the mono atom, I mean ideal gas, or if it's the non-ideal gas. This is the answer given by Gemini, you know what I'm saying? Because I already told you, do not consider just ideal gas. Ideal gas means what? It's just a single atom with no feature, no geometry feature of the atom. Okay, that's the ideal gas. But I'm trying to give this question to ChatGPT or Gemini. Yes, that's what they say. Okay, if it's the ideal gas, the gamma is 1 point something. If it's real, so it's probably something like that. Okay. I know that you are doing something. You are using some student using Gemini. Don't do this, okay? Because eventually, if right now, as I mentioned, if you the purpose for you can see the class, the homework, and you will know that midterm is not very complicated. It's just about fundamental concepts. Okay, if you still rely on the AI to do this kind of fundamental concept, what's the use of you in the future, right? But I'm reasonably, I'm trying to, I'm seeing quite a lot of discussion about AI. You know, what's the difference between AI and the human thinking? I mean, one thing is that the reasoning. Okay, so so far the AI still do not have. I'm not expert on this, right? But it's just what I'm listening. So they do not have the capability to reasoning to understand the reason and the result. This correlation. Okay, they only know the correlation. Okay, they only know that the student wants to go to that professor's class, but instead of the other one. Okay, they build up this correlation, but they do not know why. Okay, but you can tell why, right? That's the reason of the difference. Okay? So in other words, you can see the principle there, but probably although the AI can do the derivative for you, but doesn't know the reason. Okay, and for that, because of that, sometimes you can make a mistake. Okay. And the other thing that I heard, that you are using the AI to read the manual, right? Don't do that, okay? You give you wrong answer. Okay? Try to go through it by yourself. Anyway, so but the other thing is that you should not struggle too much. You know what I'm saying? I mean, while AI is going to replace you? I mean, eventually probably yes, okay? Because AI have the infinite lifetime, but for us, you just suffer tens of years, that's it. Anyway, let's go back to it. All right, so you can see that I have so many pages on my desk. So this is all I'm going to cover in your midterm, okay? So the first page is useless introduction. Basically, it's just an overview of the class, so we don't have to worry too much about it. Okay? This one is just like I give you a brief discussion about what I'm going to talk about, okay? For you, I'll give you an outline, outlook. For me, just a lazy class, I don't want. Okay? The second one, we start to talk about the first law of thermodynamics, okay? And for that one, we start to introduce some key concepts, okay? The first and most important thing, I put the key, the chapter in this side. I'm going to go to detail on the other one, okay? So the first most important thing is the first law of thermodynamics. First law of thermodynamics. So the first thing, we introduce two concepts, okay? Two concepts. The most important concept is we need to distinguish the thermodynamic parameters. And the process parameters, okay? Or process quantity. We don't call it parameter, because it's quantity. It seems that we have last person this time. Everybody here pass. Okay, so the difference between thermodynamic parameters and the process quantities are there. Whether this one is the definition of thermodynamic parameter is defined only by the state of the thermodynamic system. Okay, it's independent of the process. Okay, that's the reason we call it thermodynamic parameter or system parameters. Okay. What's the example of the thermodynamic parameters?
Oh, yeah.
What's that? Pressure, temperature, whatever, right? The pressure, temperature, volume. This is something very easy to measure. Of course, eventually after class, we know that what's going on with the spring. We have the internal energy, enthalpy, entropy, Gibbs free energy, the Helmholtz free energy. It's used A in the textbook, right? But in some textbook, it's used F. It doesn't matter, so we just follow. Okay. So that means if the state of the system is determined, all these parameters are. What's going on with
Yeah, that's bearing or something is happening to that scheme of this.
It's determined, okay? But for the process quantity, and from the name you can know that it depends on the specific process, right? So, it's what?
Heat.
Is the work, right? Heat. Okay, that's two examples we talk about in the class. Of course, we have more, but specific to this class, we just talk about it. Okay? But for most of systems, yes, we still talk about this too. But of course, you have something else, for example, like magnetic work, like the electricity, but that's not the focus of the class. But we should know that we still have something else, okay? And regarding, but of course, the thing is, in the for the process quantity, it depends on the specific thermodynamic process, right? Typically, we have no idea, okay? Typically, we have no idea. But if the process, we can call it the reversible process, okay? If that is a reversible process, then we know that the delta work equals to P dV, correct? And then delta Q equals to TdS. correct? Right? And you can write down these two equations only if the process are reversible. Okay? But how do you know whether the process are reversible or not? That means at each specific moment during the thermodynamic process, the system are under thermal equilibrium. Okay? For example, if you have a tank, okay? We press its piston very slowly. That means at each given moment, the pressure inside is uniform. The temperature inside is uniform. Okay? But otherwise, you cannot write down this one in such a way. Okay? Because we simply do not have definition for pressure of the system. We simply don't have temperature definition of the system, right? Because they are not under the thermal equilibrium. Okay? And the other feature of this kind of the reversible process is that you can draw the thermodynamic process in this PV chart. For example, we talked about the camel, circle, right? We can draw it like this, right? And in the for your homework, you know that for the TS, we can draw that these two are equivalent, right? But you can see as long as you can draw this kind of chart in this kind of diagram, in this frame, typically it's reversible. Okay, otherwise you cannot draw something like this. Okay, because you have no definition on T, you have no definition on T. Okay. Engine, the car engine. Do you think that the engine of a car is a reversible engine? No, right? Because it's so fast, right? You can see that if you see the fast video, see what's happening in the piston. You can see some part got ignited first, and the bottom not got ignited. Right? I mean, the gas and air mixture always got ignited around the plug, right? So then it's not the thermodynamic, it's not the reversible process anymore, right? Because you can see some part of the cylinder is hotter than the other part, right? But we cannot find the uniform temperature or pressure for the entire system anymore, right? And that's the reason why this kind of the ideal engine that doesn't exist, because you need to make the thermal process so slow, it's become useless, okay? But this model is help us to build a model. Basically, this is the first very important concept we talk about in the thermodynamics. And then the key idea about the first law of thermodynamics basically is the conservation of the energy, okay? So the internal energy, the change of the internal energy actually equals to delta Q minus delta T, right? Remember for this one, we use the negative sign based on because we are defining work performed by the system to the external world. Okay? This is doing work to the external world. Then the internal energy drop down. Okay, that's the reason we have negative sign. Okay, but you can use the other definition, doesn't matter, but this is the preferred. Okay? And for the reversible process, we have this one. Okay? So this is basically that's the key idea of the first law of thermodynamics. Okay?
That is the internal energy is the general one, right? General term. That is the specific for reversible process.
For the reversible process, you can write in that way. Because for the reverse, this one is, yeah, you're right. This is the general one.
Yeah.
This one, for the reversible process, you have this expression. Okay? But one thing you should understand is that for the reversible process, we can only calculate the reversible process, right? Mm-hmm. So if we are talking about not like the unreversible process, I simply cannot give you any question because nothing can be calculated. So I have to give you a grade, I have to give you a score, then everything should be reversible. Okay? Okay. And then from this one, we will understand that basically, by writing this equation, as we emphasize again and again, so if we write down this equation, we naturally select the S and the T and the V as the independent variables, right? As an independent variable, okay? Correct, everybody? All right. So one thing I want to, I did not follow it strictly follow the flow, okay? It's become useless. I will introduce some concepts in the following chapters, okay? Still remember, we're talking about how many independent parameters we need to use for this kind of for this system. We need at least 2 parameters, right? That means the degree of freedom of this kind of system is 2. right? What's the reason for that? Remember we're talking about the Gibbs phase law? The degree of freedom equals to what?
The phases
The phases
minus the amount of components.
minus the amount of component plus 2, right? Is that right? Okay. So right now we are talking about this. If we talk about ideal gas, okay, how many phases do we have? We only have one gas, right? And one phase, right? So that means the degree of freedom is 2, right? So that's the reason we always need 2 parameters to describe the state of the system, right? This is the Gibbs free energy. Yeah.
Wait, so what's a component versus a
Component means that we have how many different types. For example, if you have a hydrogen mixed with oxygen, then the component is 2, right? But for the ideal gas, we only talk one type of gas, right? But later on, when we talk about phase diagram, we have liquid phase, we have A component and B component, then some changes, okay? So, but for here, I just tell you that why we have 2 parameters for the ideal gas discussion. Because of that, okay? All right.
So
So-
internal energy be any variation of S, T, or V?
Huh?
You have a U, S, and V. It could be any variation of like S, T, and V.
Yeah, you can. You can. But what I'm just saying that for this process, we just naturally select this S and V as the variable, independent variables, okay? But of course you can change, okay? You can change. But the one thing you should be very, very careful. Okay, I did not mention that in the class, okay? I can mention it here. I mean, I think right now we already introduced all the concepts, okay? Be very careful. Remember that intrinsically we use these 2 parameters, okay? That means what? That means if the system has a constant, during the thermodynamic process, has a constant entropy and has a constant volume, then the stable state has the minimum totally internal energy, okay? If we do not change the volume, if we do not change the entropy, the system, the state of the system is a state which gives us the minimum energy, internal energy. Okay? Other points?
If dV is positive, then it will be
Yeah.
more or less, right?
Yeah, because this is the second law of thermodynamics. Remember, if we consider second law of thermodynamics, it's something like this, right? So that means this one always minimized. If we have a constant S, if we have a constant V, that means the du naturally, spontaneously, always smaller than 0. That means if the process can happen spontaneously, then it's always reach the minimized internal energy. Okay? Only if the prerequisite is the entropy doesn't change, the volume doesn't change, then the internal energy should reach the minimized. Okay? This is just go back to the classical mechanics, right? So if we do not consider entropy, the energy reach the lowest state, right? Got the points? Okay, then we can change the objective. Remember, so this is for this case, okay? If the S is constant, V is constant, then we have du. We know that for this state, we minimize the energy. But what about, but as I mentioned, what about for the states that when we do the experiment, when we synthesize new materials, when we study the alloy, typically we do not care about change in the volume. We perform the experiment under constant pressure, right? So we want to know for example, under constant entropy and constant pressure, which parameter can be minimized or maximized. Depends on which parameter can be minimized or maximized in order for us to determine the states, final states, okay? And then we talk about this one, okay? We introduce another parameter, okay? Thermodynamic parameter, U plus PV, right? U plus PV. And then the DH equals to what? The TDS plus VDP, okay? And if you consider the second law of thermodynamics, we have something like this. Correct? We have something like this. That means if a system have a constant entropy and a constant pressure, then we minimize the entropy of the system. That means the state which gives us the minimized entropy is the stable state. Correct, everybody? In other words, if the entropy doesn't change, pressure doesn't change, the spontaneous process lower the entropy of the system. Correct, everybody? Right?
Say it one more time.
If the system has a constant, if the system has a constant entropy and a constant pressure, then a spontaneous process will lower the entropy of the system. Correct, everybody? If the system, let me write down for you instead of repeating. If S, V are constant, spontaneous okay? If S, T are constant, a spontaneous lower H. Okay? What if T and V are constant? Which parameter got reach the lowest value? If T and V are constant, then which parameter response? Huh? S, yes, but not only S. Huh? Which one? If T and V are constant, which parameter? A. Okay. The host, home house, free energy. Okay. What's the reason for that? A equals what? U plus minus TS, right? Then the A equals to what? Minus SDT. Minus P. Yeah. Oh. No, what about if the T and P are constant? Gibbs free energy. Okay, that's the reason when we talk about phase diagram, we always found which system give us the lowest Gibbs free energy. The reason is we are considering under the constant T and the constant P situation. So the Gibbs free energy got the lowest value. Okay? If we are talking about something that the T and V are constant, then we need to find a state which give us the lowest, the Helmholtz free energy. If we're talking about system, under the constant entropy and constant pressure, we need to find the lowest entropy. Okay? And for system has the constant entropy and constant volume, we need to find the lowest internal energy. Okay? That means it really depends in which situation you are considering the balance of the system. Okay? And for most of the cases, as I mentioned, we consider temperature and pressure. So that's the reason for the material science, we typically use the Gibbs free energy. Okay? So we do not mention this one in the class because at that moment we have not talked about this one. Make sense? And I hope that this one can give you another perspective why we define so many thermodynamic parameters. Because we want to use them for different scenarios. All right. And then in this chapter, we did some practice, not too much, because I mean, one key idea is that because the H, G, U, and S, whatever, they are thermodynamic parameters and only decided by the final inertial state. That means if I, for example, if I want to ask you to calculate the change of the entropy, okay, of the system, but you do not know what the specific process can link this initial and the final state. Basically, you just artificially build any kind of loop. Okay, even these processes are not reversible, but you still can link these two states, the initial state with the final state. Even this process is not even the actual thermodynamic process. For example, like combustion chamber. Okay, we mentioned this is not reversible process. Although they are not reversible, but since this one is the thermodynamic parameter only decides, the change only decided by the initial and final state, you can always link them through any reversible process and do the calculation, which calculate the change of the entropy, the change of the internal energy, change of the entropy. Okay? Got my points? Okay, so basically that is the key components for the first law of thermodynamics. And of course, during the discussion, we also introduced the ideal gas equation. Okay? I think this one should be very clear. Okay? And in that process, we also introduced several very important reversible process for the ideal gas. Okay, we introduced several reversible processes. For ideal gas. Okay. Right. We mentioned about the, for example, like the constant pressure, the isothermal process. Okay, basically for the isothermal process, PV equals constant. Okay, this is isothermal process, right? And we also talk about the adiabatic process, okay? Adiabatic process. Okay, and then we have this equation, right? So you should better understand how can we get this equation. Okay, how did we eventually get this equation? Okay. And the other important conclusion you need to remember is the CV equals to what? R. And CP equals to R, right? I mean, I told you this in the class. I think I mentioned, but not too much. This is the consequence. I mean, we can calculate this one, right? Why it have this very, very beautiful expression? Because I mean, this ideal gas, we can precisely calculate the the heat capacity of them. Okay, from we call it the equipartition theorem. Okay, so if you feel interested, just go back home and recheck it again. Okay, equipartition theorem. Partition theorem. Okay. This one will not be covered. I mean, the midterm will not include this part. Okay, no, it's too much. Okay, it's so much the fundamental calculation. You don't worry too much. But if you're interested and want to know how we get these two numbers, you can go there. Okay, but this one will not be covered in class. Will not be covered in the midterm. But what you need to do is to remember these two numbers. Okay, so basically that's the key information of first law of thermodynamics. But of course, I only give you the most important key, knowledge point. But you also need to do some practice about the calculation to calculate do some calculation of how the pressure change, how the volume change, how much heat is going to absorb from the process. Okay, by using the ideal gas equation. But you can see that for most of the class, we only focus on the ideal gas. The reason is ideal gas is the only field, I mean, the thermodynamic systems, we know everything, every details about it. But if you go to solid, go to liquid, it's become more important, it's become more complicated. Okay, the reason is for the ideal gas, we do not consider the interaction between atoms. Okay, there's no interaction. Okay, the entropy is only configuration entropy, and the energy is only thermodynamic energy. It's only that kinetic energy. There's no potential energy. Okay, but if you go to liquid, we know that things become more complicated. Right? Okay, this is the first law of thermodynamics. Then we move on to the second law of thermodynamics. There are several descriptions about the second law of thermodynamics. Basically, you can see that for the spontaneous process, the entropy always increase, and you cannot extract the heat from you cannot extract the heat and change it to the work from the single heat source. Okay. Remember, the number of heat sources is very important. I already mentioned last time that it's possible for you to extract heat and change extract heat from low temperature to high temperature heat sources. Yes, you can if you have multiple heat sources. But if you have two, no. Okay. And the same thing, can you change heat into work? Yes, you can. But you cannot change heat from a single heat source into work. Okay, the number of heat sources is very important. So or you can see that the second type of the perpetual machine doesn't exist. Something there are quite a lot of different kind of express, but you have to be very careful. Okay, there are so many details in different kind of the expression. Okay, but the safest one is if you don't want to struggling with this kind of very tiny, the word in this game. Just say that, okay, the second law of thermodynamics tells us for the spontaneous process, we always have always increase the total entropy. Okay, that's part of the safety statement. You don't make any mistake. But okay. And during the class, if you check the class note, I mentioned that for spontaneous process, we always lower the energy, but we also need to consider the steady state behavior because it's a multi-body system, right? Then we need to consider the like the distribution of steady state behavior. Okay, that's the reason we introduced this concept of entropy. Okay, I don't need to discuss why we have this parameter anymore. And we also need to also mention that we already mentioned that for the if the entropy is constant and volume constant, we lower the U. Okay, but if not case, we have some other parameters. Okay, and basically for all thermodynamic processes, one thing you have to keep in mind. We always have two parameters or two factors competing with each other to give us equilibrium states. One thing is the statistic distribution. Okay, the state should have the internal energy as low as possible, but it also should give us a reasonable possibility for this state to be observed. Okay, got my points? So, and then that's the reason for the Helmholtz free energy, we have it this way. Okay, so basically we have two factors that we competing with each other, right? One is the total internal energy, the other is the thermal distribution. Okay, we have to consider both factors. So that's the key concept of the second law of thermodynamics. Basically, we introduced the concept of entropy, and we know that for the spontaneous process, the entropy is always maximized. So regarding so we did quite a lot of progress. We did quite a lot of the practice to calculate the entropy change in different processes. Okay, and the key conclusion, we always know that for spontaneous process, this is always larger than zero. I give you so many examples. Okay, and definitely this one will show up in your exam as well, and I think it's also show up in your qualified exam, right? Correct, everybody? For any kind of spontaneous process, the delta is larger than zero. But be very careful. One thing is, this spontaneous entropy is the entropy of the entire system. We not only consider the thermodynamic system itself, we also need to consider environment. Okay? We also need to consider environment. For example, you have a heat exchange or something. For example, you have a cup of hot water, Okay, 100 degrees Celsius, it's not spontaneous cool down. Okay, then that means the entropy of this cup definitely spontaneously reduced, right? So then you cannot say, but you cannot say this disobeys the second law of thermodynamics because you also need to consider the environment, because the environment can change the heat with it. And then you can see that if you consider environment, then the total entropy goes up. Got my points? So if you want to use this one criteria to determine whether this process is reversible or not, or whether it's spontaneous to happen or not, you need to consider the entire system and environment. Okay? But what if I do not care about the environment, I only care about system inside, then you need to consider this one. Okay? You need to use this one to determine whether it's a spontaneous process or not. Okay? So for that one, the ds can only refer to the ds of the system, and the du is only the internal energy change of the system. Okay? If you use this equation to determine whether it's spontaneous or not, you do not need to consider environment. But if you consider environment, but if you want to use that one, you need to consider environment first. Okay? Got my points? So when you go back home to see all the practice we discussed in the class, we talk about the mixing of two types of gas. We talk about the heat sources. They put together. I think for your qualified exam, you also talk about a piece of copper rod put together. So with the change of the entropy. Okay. Yeah. I think that's the pretty much the second one, thermodynamics. Although the concept are complicated, but the key idea. We only have that one. Okay? But the other most important thing, as I mentioned, so for the spontaneous process, well, I already mentioned, but I want to repeat again. So for the spontaneous process or non-reversible process, typically we cannot draw this one, right? I already mentioned we cannot draw a chart in this PV diagram or TS diagram. Typically we cannot do the draw, right? But we still can calculate the change of the entropy, right? By what? So if I tell you, so we have the initial state, we have the final state, but we link them through a probably free expansion process. Okay, it's not a reversible process, but I still want to calculate the change of entropy. How will we do that? We just find a reversible process to link these 2 points. Okay, to link these 2 points. Basically, we find a virtual loop to replace the actual loop and do the calculation. Okay, because of what? Because again, the S is a thermodynamic process parameter, only determined by the final and the initial state. Okay, and the loop is not. You have different loop. You can use any kind of loop to link these 2 states. Okay, got my point? And then you will find in any kind of loop, eventually you give the same delta S. What's the reason for that? How can I prove it? That you can link the initial and the final state. This one is the V, this one is P. Okay, you have the initial state, you have the final state. Okay, we can, if I want to calculate the delta S, you can link this one with the root 1. Okay, you can also link them with another root. You can also link with another one. Okay, but all of them, eventually through the calculation, you always get the same delta S. What's the reason for that? How do you prove it? How do you prove it? Mathematically, how do you prove it? How do you prove that any kind of the reversible process link I and F, final and the initial state? Always. What's that?
Shortest distance between them.
No, there's no short distance. It's not the geometry problem. It's the dynamic process. How do you prove that all this loop give you the same change of entropy?
Is it R times ln of whatever your final was over your initial, or
No. What was it? What are you saying?
do an integral?
Okay. Repeat again. So from this can be proved from the Carnot cycle. Okay? So the idea is, so we can calculate the entropy of change from the Carnot cycle, right? We know how the entropy change, right? So if you can find the process, if you can find any kind of loop, okay? If they do not have the same delta S, okay? That means you can always find a loop. Think about it. This loop, you can always fill them with a lot of number of the kind of cycles, right? But if you can find a state showing the different change of entropy, basically you can build up another loop with a higher thermal efficiency than the Carnot cycle. That means you can pump the energy from low temperature to the high temperature. You only have two heat sources, okay? You know what I'm saying? That is the basic law of thermodynamics. Okay? Basically, while the final and initial states have the always, the analytical loop give you exactly the same change of entropy. This is because the second law of thermodynamics. Okay? Follow my points?
Once more, please.
Okay. Let me consider this way. Be more quantitative, okay? This is I, this is F. So we know that this one is a reversible process. So what's the definition of the reversible process? D delta Q equals to P ds. Right? Correct, everybody? Or you can see that something like the we have the, for example, this one is at T1, this one is at T2, right? I should leave this one in your midterm instead of prove that in the class.
Do both.
Okay, I give you one question. This will be in midterm, okay? I
Are
already disclosed one question. You need to prove that any loop, as long as the loop are reversible, they should give you that same delta S, okay? This is one question in your midterm. Why am I bothering to do that by myself? You're going to do it.
Is it already on the midterm, or is it going to be on the midterm?
It's going to be on the midterm.
And are we allowed to watch the video during midterm?
You can, but in the video, same thing.
Oh.
Okay? Your video will start, oh, the midterm will be this question. Okay, this is one question in midterm. Oops, I don't want to prove myself. I'm so lazy. So you already got one question, okay? Good, good. I'm so smart. Okay. So on the second law of thermodynamics, actually the most important concept, the other most important concept in the second law of thermodynamics is the Carnot cycle. Okay. So basically, this one is you can prove that one with the Carnot cycle. Okay? Basically, the logic or the argument of the Carnot cycle is like this. So first of all, we artificially create a thermodynamic loop, okay? And this loop formed by two isothermal process and two adiabatic process, right? And I think in your homework I already mentioned, you already know that we can also draw this one in the ST diagram in that way, right? But before we define the S, we draw in that way. In the PV diagram, we draw the kind of cycle in that way. And we just do a lot of calculation. You can go through it yourself to see how we do the calculation, all right? Just by doing the PV equals to constant first, I mean PV gamma equals to constant for the, this is for the isothermal process, this is for the adiabatic process. You can calculate the efficiency of the engine, okay? But eventually, we will know that this one is a heat source one, this one we can this one hot source, this one is the low temperature source. So eventually, the heat you absorbed from the high temperature heat source divided by the high temperature equals to the heat released to the low temperature heat source divided by the low temperature heat source. The temperature of the low temperature. This is the relationship between them. Okay, and then of course the work done by this process is a QH minus QL. Okay, and then from that one you can calculate the efficiency. The efficiency is just simply like efficiency. Is that right? Okay, so, and you can see that because the entire process, we have this one. We have this one. If we make the Carnot cycle very small, then if this is only very tiny process, then this become like this, okay? The DH, the T, or let me change that. So for this equation, we can change it to this one, okay? TH minus TL. Okay? We know this one is absorbing the heat, this one releases the heat, okay? And then we can add this one like this, okay? So basically, we don't worry too much about sign of the system. If this is negative, that means release heat. If it's positive, become absorbing heat, okay? Then we can just put this conductive sign into the heat, okay? For the calculation, if you find this one is negative, that means released heat, okay? And then you can see that the entire process actually eventually will become, if you have a multiple heat source, if we have multiple heat source, eventually it becomes something like this. Okay? It's become something like this, okay? And then we can find that through the entire process, this one equals to 0, right? And then we have something, this one equals 0. Okay, if we only consider a very tiny process, then eventually we have something like this. Okay? Okay. You can see that the dq divided by t always show up in the entire calculation. That's the reason we define this parameter as the ds. Okay? We define as ds, and we call it entropy. Okay. Got my points? And you can see that for this kind of reversible process, we always have the delta S equals 0. Okay? That is a reversible process. Got my points? And for the non-reversible process, we always have an efficiency lower than this one. Okay, for the non-reversible or spontaneous process, we always have efficiency lower than that one, and because of that, the delta S always larger than 0. Got my points? And remember why we're saying that for the reversible process, we always have the efficiency lower than the Carnot engine. The reason is, if we can find another engine, reversible engine, has the efficiency higher than the Carnot engine, we can build up a loop, okay? We can build up a loop. We have the high temperature, we have the low temperature heat source, okay? And then we have the Carnot engine here, and we give out the work. If we can find another engine, for example, like the Dr. Lay's engine, can have a high efficiency, that means we can use this work to pump heat from low temperature to high temperature. And then if we see them together, then we can spontaneously pump heat from low temperature to high temperature. Right? This is the second law of thermodynamics. That's the reason for the Carnot cycle will give us the highest thermodynamic efficiency, okay? And we can generalize it. Any kind of the reversible engine always give you the same efficiency. Okay? Any kind of engine always give you the same efficiency. What's the reason for that? The reason is, for any kind of engine, any kind of reversible engine, okay, for any kind of reversible engine, any kind of the thermodynamic cycle, any kind of thermodynamic cycle. Come on, I already proved that for you guys. Any kind of mechanical cycle, as long as you can draw the figure on this diagram, this is a reversible process, right? As long as it's reversible, we can always separate them into a lot of very tiny the Carnot cycles. Correct, everybody? So each of the Carnot cycles give you this expression. Then the integration of the entire area also gives us the same conclusion. Understand what I'm saying? That means what? That means if you do the integration of the entire one, should equal to 0, right? Should always equal to 0, right? And you can see that if you go back to here, this is random shape from this point to this point. If you only carry this point, if you do this kind of integration from this end, it should always equals to the integration of this end, right? Since the initial and final temperature are the same, so the delta S equals to 0. Right, so I already proved that. So this question disappears in your final in the midterm. Okay? I already solved that. Before you memorize that, just you read it very quickly, so you have no time to write it down.
The class is already recorded.
What's that?
That's
recorded.
Your final exam will be in
You
class.
guys are welcome.
I will have the in-class closed book final exam for everybody.
No, but it was not our
If you can
mistake.
prove that you cannot memorize, I
It was
will.
not our mistake. Right?
Forget about it. No, don't waste time on this kind of nonsense joking, okay? I will keep warning you. You have so many things to cover. Okay? So basically, that's the second law of thermodynamics, okay? I'm not going to ask you to prove it, but I can ask you to do some calculation, okay? But the key point is, you can link the 2 points with any kind of the loop, okay? With any kind of loop. Anyway, so, and then for the next part, I mean, following the second law of thermodynamics, we talk about something about the statistic thermodynamics, okay? Basically, we spent a lot of time on it. The main purpose or the main concept we introduced in this section is we introduced some concept, right? We talk about the microstate. The microstate basically the state that can be described as the P, V, S, T, whatever. So we use this kind of the macro parameters or thermodynamic parameter to describe the state, right? But what's the reason, but what's the physical meaning of it? Then we introduce a concept. For each of the microstate actually is corresponding to a distribution, okay? Distribution. We introduce the concept of energy levels, that means how many particles in each of the n level, right? And then in order to calculate, then we also talk about what is the distribution has the highest possibility, Right now we know this kind of the distribution gives us the highest possibility is the Boltzmann distribution, right? Something like this. So the number of particles is proportional to the energy of this energy level divided by kT, right? This is the Boltzmann distribution. Basically, we have the number of particles, we have energy, then we have more particles, just the concentrated on lower energy part, but we still have some particles have high energy. You know what I'm saying? Then it's just like in the class, always some students want to be very active, but most of them just keep silent. Okay, so this is the thermal distribution. Okay. And but how do we know whether this distribution is more preferred or this type of distribution or some other distribution more preferred? We introduce a concept we call the most probable distribution. The most probable distribution is the one gives us the highest number of the microstate. Okay, the highest number of the possible microstates. Correct, everybody? We introduce the microstate. That means it depends on the specific configuration of how many atoms or how many particles in the specific energy level and how we arrange these kind of particles, right? So this is the microstate. Basically, the microstate underneath, above the microstate is the distribution, and the distribution decides the microstate. Okay? Got my points? So basically, the microstate is given by distribution, and the distribution we observe is the most probable distribution, and which has the largest number of the microstates. Okay? And then the entropy is just it's defined that way. Okay? So this is the Boltzmann constant times the ln times the number of the microstates. Okay, right now we find out the main purpose we talk about that section is to give you this expression. Okay, to explain what is the physical meaning of the entropy. Okay, basically entropy is a measurement of the microstate. Okay, and the other way for us to remember this definition is, first of all, we know that there's a constant. Okay, there's a constant. But why we do not define something like this? Instead, we define something like this. Why we do not define that way? We need to introduce the law in here. What's the reason for that? I'm not talking about mathematics, but I'm talking about logic. Why we have the law in? The reason is, huh?
Because it's always supposed to be positive?
That's one reason, but it's not the only reason. The reason is we're talking about entropy. Entropy is an extensive parameter, right? It's an extensive parameter, right? But you know that the possibility, for example, if I have one tank, if I have one particle in each of tank, for example, previously we have one particle here, we have one particle here, so we only have one configuration, right? Right now combined together. We put these two tanks together. Now how many possibilities we have? We have this possibility, we have this kind of possibility, we have this distribution. Okay? That means as the space increase, the possibility not increase, I mean the number of microstate doesn't increase proportion or linearly. It's increase, I mean the exponentially. It's increased exponentially. Or more precisely, it's increased is a fractional, right? So because of that, I just add a line to make it linear. Okay, that's the reason we change this kind of the nonlinear parameter to a linear one in order to make this parameter an extensive parameter. Okay, got my points? That's from mathematical point of view why we define that way. Okay, that makes sense?
We can say like it follows Boltzmann distribution, so
Yeah.
that we use long.
Yeah. Okay, we play this trick all the time. Okay, whenever you see this kind of fractional, we add a line there to make it linear. Okay, and we use this kind of, we call it the Stirling approximation all the time. Okay, just make this kind of the thing to be make it linear. Okay, to make sure that the entropy is an extensive parameter. Okay, make sense?
I have one question. Extensive parameter, just the definition of that is that-
Extensive parameter, for example, like a volume. An extensive parameter means it's proportional to the number of matters.
Okay.
Okay, and we also have intensive, that is independent of the number. Temperature, pressure, that is intensive. Okay, no matter how many matter you put in there, the temperature is still the same. It's independent of number of matter. But for the energy, entropy, volume, they are extensive. Okay? Got my points? Huh? What's that?
Some difficulties to understand.
Some difficult to understand the question. Let me give an example. So the I have no idea. I want to give you another example, but I don't have the example coming in my mind yet.
Density versus mass.
It's not a good example. I want to give more specific example. What is the intensive? What is the anyway? I don't know. All right. So then, after all of, we already mentioned that one. Okay, the fundamental equations of thermodynamics. Okay, and then the next chapter we talk about is the fundamental functions or equations. Okay? We talked about that. So and I'm going to talk about the first law of thermodynamics just now, okay? I already mentioned we have four, right? We have the internal energy, we have the enthalpy, we have two types of free energy, okay? And I already mentioned in which kind of scenario, in which kind of condition, this parameter got minimized, okay? Okay, for U, we have this one, du equals to PdS minus PdV, okay? And dH equals to PdS plus VdV. Okay, and the dA equals to minus SdT plus minus dPg, and G equals to minus. Okay, we have totally four relationships. Correct, everybody? Okay, and I already told you why we have this one. We have these four parameters, okay? Once again, don't waste time. Just check the video. I already mentioned, right? Why we have this one. Anyway, so from this one, we also make use of the continuity of the functions. Two variable functions. We can also do the second order derivative of each of them, right? So in that case, so if we do the second order derivative of the equation, first of all, from this one we will have, for example, we just use this energy, okay? And from this equation we know that T simply equals to partial U, partial S as a constant V, and P simply equals to partially U, partial V as a constant entropy, right? And if we can do the second order derivative, continue to do that. Then is the partial T, partial T, partial what? Partial V, constant entropy, right? And then this one, and equals to partial S, partial V, okay? And then we have this one, partial P, partial S as a constant V. This one equals to partial U, partial V, partial S. Okay? By using the continuity of the equation, we know that we can switch the order of this derivative. So this one, these two terms should equal to each other. Then we got the Maxwell relationship, right? We got the Maxwell relationship, the partial T, partial V, S simply equals to partial P, partial S, V. Okay? This is the first Maxwell relationship. And by doing the same thing to the following, another three equations, we got the other three Maxwell relations. Correct?
Shouldn't there be like at least like 16 Maxwell relations?
Why there's 16?
Like or more?
If you can define more, if you can find more parameters, yes, you can. For example, if this is not PV system, if this is a magnetic system, then we have the UTVS minus mu dm mdh. You have another Maxwell equation. It depends on what type of system you have. Okay? But the principle is the same. Okay? And as I mentioned, so the one main use of the Maxwell equation is to change some unmeasurable parameters in terms of measurable parameters. So we can do the calculation. Okay? For example, we mentioned that in last class, right? So if we want to know how the entropy change as a function of V as a constant T, so because we don't measure the entropy directly, we cannot measure the entropy directly. So we can change this relationship to partial P, partial T. Okay, P measurable, T measurable. So we know how the entropy change. Okay? And we did, of course, we did quite a lot of practice how to change the different parameters, right? Now, last homework, we have 2 questions about it. Correct, everybody? All right, so basically from here, all these 4 parts, we build out the foundation of the thermodynamics. Okay, and all the following discussions are using these 4 chapters, the knowledge from these 4 chapters. Okay, that's the most important part. And the following, we just make use of them to solve different problems, okay, to analyze different systems. Okay, you can see this one is the first block of the semester. And the second one, following that, we start to talk about the equilibrium, okay? We start to talk about the phase equilibrium. Yeah. We should talk about the phase equilibrium. And then once again, since most of the process we are talking about, what we care, happens at the constant temperature and constant pressure. So which parameter we use to describe the stability of the system? We use the Gibbs free energy, right? correct? Because if the T and the P are fixed, then for a spontaneous process, we always minimize the Gibbs free energy. Correct, everybody? So that's the reason we use the Gibbs free energy to determine why a phase transition happens or not. And we also give an example. We start the discussion from the simple liquid to gas phase transition, okay? Because for the gas, we know that the Gibbs free energy equals what? The internal energy minus the enthalpy minus Ts. Correct, everybody? Right? And then we know that we know that for the gas, entropy is higher, right? So that means at the high temperature, at the low temperature, okay? At low temperature, so at the low temperature, the entropy of we know that the system in the low temperature is in the liquid, right? In the liquid, and as the temperature goes up, this term becomes more dominant. That's the reason the Gibbs free energy drops down, right? Correct, everybody? So this one is the liquid, right? And we also know that the gas has a higher entropy, That means it drops down faster, right? So then we have gas looks like this, correct? We don't have gas phase, we got vapor, okay? That way, right? And you can see they start to cross to each other. That means at low temperature, the liquid phase is preferred, and at high temperature, the gas phase or vapor phase is preferred. And this point is the boiling point, right? So by this kind of simple analysis, we know we can understand why the phase transition or phase transformation happens. Correct, everybody? But this one is not enough for us to understanding this only from a thermodynamic point of view, explain why the phase transition happens. But we still do not know the kinetic process, right? But we know that for the ideal gas, we shouldn't have this phase transition, right? Because what? Because ideal gas, we don't have the change of the entropy, right? Because there's no interaction between each other. That's the reason if we want to liquefy gas, it must be non-ideal, right? It must be non-ideal in order to give you the change of the entropy. Then we start to talk about the behavior of actual gas, right? And we build a model we call it the Van der Waals model, right? Van der Waals equation. So we can use that one to analyze the phase transition. Okay. So I think for this chapter, I may give you some calculation questions, okay, about the Van der Waals equation. Got my point? Got my point? Okay. All right. So then this is something we need to talk about. Okay, that's the way in the phase transition. But anyway, so and the other very important conclusion is like this. This is the point of the phase transition, right? And you can find that. The vapor phase and the liquid phase share the same Gibbs free energy at this phase transition point. Correct, everybody? Because when the Gibbs free energies start to cross each other, this is the point, the critical point at which the phase transition happens, right? But you know that this is only a simple single component system, right? But if the number of particles change, then this equation doesn't work, okay? Then we use the chemical potential, okay? We only talk about the molar, okay, because the number of particles can change. Then we don't care about the total entropy anymore. We talk about the molar entropy, and the total Gibbs free energy. We start to use the molar Gibbs free energy in order to consider the particle exchange. Then in the thermal equilibrium state, under the phase equilibrium, we always have the chemical potential equals to each other, okay? And more precisely, we know that we have the dG equals to, for example, we have the vapor phase, okay? dG equals to what? Equals to minus SDT plus VdP. That's VdP, right? and then minus plus mu v dn. Okay? And then we also have the d, this liquid phase, still minus this v, this v. Correct, everybody? Right? Again, since that on this kind of equilibrium states, we have this equation, right? And then we have d and d equal to each other. Correct, everybody? And then these two equations should equal to each other, right? And also, in the equilibrium states, as I mentioned, we only consider a constant temperature pressure situation and constant pressure situation, right? And these two terms we can ignore because they don't change, right? And then that means under the thermal equilibrium, we have dV dN should be equal to mu, okay? And then the chemical potential should equal to each other, okay? Got my points? So that is very important scenario for the under the. This is very important relationship under the thermal equilibrium during the phase transition. Okay, if the two phases are in thermal equilibrium, the chemical potential should equal to each other. Okay, should equal to each other. Got my points?
Very forward. From where this equation comes.
There's no equation coming from. It's dg. This is definition.
So similarly, the entropy and the volume at the phase transition point.
No. Entropy and the volume is not necessarily the same.
But if you vary the entropy, then the volume term would not compensate for the variation of the.
It does, but that's the reason why we use the Gibbs free energy. We don't. Because since the temperature doesn't change, no matter how much the entropy changes, this term always equals 0.
Oh.
Right? Because temperature doesn't change. The pressure doesn't change. We don't consider the contribution from this term. But during the phase transformation, the particle number changes. The particle in the vapor phase will enter the liquid phase, or liquid phase is going to enter the volume phase. So the dn is going to change. So this term not equal. But if you make the dg equal to 0, the chemical potential must be equal to each other. Right? But not necessary for the entropy equal to each other. And it's not necessary for the volume to equal to each other. Because the temperature and pressure don't change. We do not consider their contribution. Okay, so that's the important thing, okay? So actually the end, all the following, even next semester as I mentioned, we talk about the phase transformation. All the phase transition problems are based on this equation, okay? Mu phase 1 equals to mu phase 2. Okay? They always equal to each other. That's the chemical potential, okay? That's the chemical potential.
What is that describing physically?
Huh?
What does that describe physically?
Physically, okay. Good, really good question, actually. So we know that under the thermal equilibrium, so what kind of we need to minimize. If we want the system to retrieve the thermal equilibrium states or spontaneously reach the thermal equilibrium states. As I mentioned before, we need to consider two factors, all right? U and Ts, okay? We need to minimize the U and maximize the S. Correct, everybody? And then, but of course, if the system, if this kind of process happen under the constant pressure, we cannot use U, we should use H, right? We should use H. Correct, everybody? H is what is the enthalpy, right? So that means for the spontaneous process in the room temperature, for the spontaneous process at the constant pressure and temperature, constant pressure, this one needs to be minimized, and entropy should go above, right? And because of that, we can define this parameter in such a way, okay? That means this parameter got minimized, okay? That's the parameter got minimized. But that means in the thermal equilibrium, we should not only consider a contribution of the entropy, we also need to consider a contribution of the enthalpy, right? Basically, this is energy, not enthalpy. This is entropy, this is disorder, right? This is disorder. And this kind of information is not only carried by the entire system, it's also carried by a single particle, right? It's also carried by a single particle. So for example, if I have phase 1 here, I have phase 2 here. So if the particle enter from phase 1 to phase 2, it will take some entropy from 1 to 2. It will also disturb the order. It's the lower entropy here and increased entropy here, right? But and that means this, and then G divided by the number of particles. This is the average. This chemical potential, in other words, is the average Gibbs free energy carried by a single particle. Correct? So if the particle enter here, the net effect, the contribution you add to this system is the mu dn. That means we bring that much Gibbs free energy from 1 to 2, right? And then, of course, the similar thing. This is 1, okay, and the mu 2, right? Then if the particle enter from the phase 2 to phase 1, it's carried that much Gibbs free energy from 1 to 2 to 1, correct? But under the thermal equilibrium, the fluctuation should happen in the 0 point. Correct, everybody? Then we should have something like this. Correct? To make sure that it's on the bottom. Right? If you have the slope, then we just then everything just push toward that direction, right? But you know that everything should be on slope. That means if I move from here to here and from there to there, roughly the same. That's the reason for the thermal equilibrium, we always have this one. Okay? That means what? That means even when I have some particle enter from phase 1 to phase 2, I do not change the total Gibbs free energy. Right? So that's the reason this condition tells us this system is under thermal equilibrium. Okay? Did I answer your question? Okay. Basically, we understand the chemical potential. Basic chemical potential is how much Gibbs free energy carried by an individual atom. Okay?
And how can something be at thermal equilibrium if it's in a phase transition?
Be something like this. That's the reason we call it chemical potential. Something like this. It's just like your bank account. Okay? Think about it. You have income, you have spending. Okay? You have every month you have some money bring into your pocket and you spend something. If you enter equilibrium, then you do not have phase transition. Okay? But if you have more income and less spending, you become richer. Okay? Then your phase transition probably go to a higher status in your society. Okay? But of course, if you spend too much and you don't have income, then you lower your status. Something exactly the same thing. Okay? Exactly the same thing. You know what I'm saying? The phase transition event, you change your status. Of course, I mean, it's not a good analogy, but you understand what I'm talking about. Okay? Do we still have time? Or still want to stay here? Anyway, so we are talking about gas. The last chapter, or last section we talk about is the behavior of solution. Okay? The solution different from gas is because solution we call is condensed matter phase. Basically, it's alloy, solid state, or liquid. Okay. The reason, as I mentioned, is that same to the non-ideal gas. If we want to form liquid or the solid, we need to have the intermolecule interactions, right? So we cannot describe this system with ideal gas anymore. Correct, everybody? So we need to consider the change of the entropy. So we introduced three different levels of the behavior. First of all is the ideal solution. That means after mixing, the intermolecule interaction doesn't change. Okay, and then from the class, we mentioned that basically that's a very strong requirement. But the more relaxed one is, as long as the AB molecule interaction has the same level of the AA and AB average, this can be still considered as be considered as the ideal solution, right? I mean that's something, right? So